Hi everyone. I'm planning to make a couple of concepts video which are very important from interview perspective. Either you are preparing for machine learning system design rounds, or whether you want to basically appear for any machine learning engineer roles. These concepts would be really helpful. And I first would like it to become a reference point for me to brush up the concepts every now and then, and I hope that it will become same for you as well. So in today's video, we will go through classification metrics, how you can choose one metrics or other, what kind of problem need particular metrics yeah, like how do you choose particular metrics for particular problem and so on. So let's start by building the confusion matrix, and then we'll derive the related evolution matrices, and then we'll discuss pros and cons, or maybe choice like when you should pick particular metric. So let's understand the confusion matrix. To build this matrix, first you have to keep your actual values, right? Ground truth values on the left hand side, as shown here on the rows. So here we are considering binary class, right? So positive and negative, and your model will also predict positive and negative since it's a binary class problem here, right? So you can anyway, if you understand this better, you can extend it to multi-class classification. But just to build your foundation, this would be a good start. So if let's say actual class value is positive, and your model also predicts a positive, then we call it a true positive. So it's very important to understand this terminology so you don't basically misinterpret, or you don't need to basically remember these things if you understand it properly. So and if your actual class is positive and your model predict it as a negative, right? So for example, someone has a cancer, but your model says no, yeah, the person doesn't have the cancer, so it means it's a false negative, right? And if let's say your actual class is negative, but model say predicting as a positive, right? So for example, if there is no cycle present in the image, but your model says it's present, right? So it's a false positive. So you can say this is kind of a false alarm, right? And if something is negative, let's say there is no cycle present in the image, and actually your model is also predicting the negative, it means it's a true negative, right? So if you look at this full box, in this there are two errors. One is this and other is this. If you get this, it's correct. If you get this, that's also correct, right? So mostly based on a problem, right? We may need to figure out which error has more value for us based on the use case. So that's why there are multiple use case, or maybe that's why multiple metrics we can derive out of this for if you understand this table perfectly. So let's say one of the metrics is useful for classification is precision. So you can derive it using this particular column. So true positive divided by true positive plus false positive. What it says is true positive divided by all the positives predicted by model, right? So if you observe the equation out of these two error, right, false negative and false positive is a part of the equation. So, if you are having any use case where false positive, if it is costly, right, it's not acceptable, then you can use the precision. So for example, spam detection problem, right, where you are classifying whether email is a spam or not, and their false positives are actually expensive, because if you mark a very important email as a spam, then it's not good, right, and as a user experience. So for that kind of problem, you can choose the precision. And what actually in layman terms we can say precision tells us. It tells us out of all the predictions, right? How often our model is right if it is predicting something as a positive. So, for example, if there are 10 cat images, right, and out of the 10, 7 images are predicted as a cat. So, we would like to know out of those 7, how many were actually correct. Similarly, you can see the another matrix for classification is recall. So what recalls usually in layman terms tells you is out of all the retrievals, how many of out of the actual class, right, you are able to retrieve. So for example, if we are searching for comedy movies and if we have let's say 100 movies in our database, and if we have predicted 30 movie as basically comedy movies, then we are trying to figure out like out of those 100 how many percent of movies we actually able to retrieve, right? For example, in case of retrieval problem. So again, if you want to derive this, if you look at true, if you look at this table, we are trying to we can get this using this row, right? True positive by true positive plus false negative. So again, as we have done in the precision, similarly, if you observe one of the error, right, the false negative is a part of the equation. So if there is any use case where false negative is very expensive for us, then you can use the recall. So for example, in case of medical diagnosis for cancer, missing a cancer case is more dangerous than false alarm. So if someone has a cancer, then we must detect it. But sometimes it's okay to say, I mean, if according to problem, if it is okay to say someone has a cancer, even if it is not, that would be false alarm. But again, there might be again few more tests could be done for that person and so on, and we can eventually figure out that person doesn't have the cancer. But if in place the first attempt itself, if you miss a cancer patient detection, then it's very expensive, right, for that problem. So for such problem we can use a recall. So recall is also known as a true positive rate. It's also known as sensitivity. So I mean, yeah, these are the terminologies you can talk for different use cases as well while picking up this particular metrics. Yeah, so it doesn't mean actually we start giving healthy, we label healthy person as a sick. So we also want to basically balance out false alarm as well in case of that particular problem. So yeah, moving to next matrix, which is specificity. So mostly I forgot to mention this sensitivity and specificity is used this terminology in terms of medical use cases, but yeah, sometimes it can be used somewhere else as well. But I haven't, I mean, found it very often. In precision and recall, we were mostly focusing on error, right? Which error it has, and if it is a costly, we were trying to focus on that particular matrix. But in case of specificity, which is true, negative, red, here we focus on true negatives. So for any problem, if we find the true negatives are costly, right, then uh, uh, we want to basically go with this matrix. So for example, fraud detection system, right? So if we want to ignore uh, any fraud, right, which is any non-fraud case, so in that case, we can use this. We can use the specificity in that particular case because true negatives are really important to catch. Another example I would like to say is maybe airport scanner scenario, right, where model is classifying whether particular bag is safe or threat. So in that particular case, if we want to Let's say out of all the flagged items, right, we want to know actually how many of them were threats. In that case, we can use the precision matrix. And in case of like all the safe items, how many did we correctly leave it alone, right? How many like items we confidently skipped it if they were safe. So for that, we can use the specificity as a matrix. Now, from this true negative rate, we can, I mean, if we just do 1 minus true negative rate, what we get is false positive rate. And this particular TPR and APR, right, true positive rate and false positive rate, can help us draw another matrix, which is called uh, receiver operating curve, ROC curve, and for that curve, if we get the area under the curve, which is also a good predictor in case of like we for us if both false positive and false negative both are important, right? In that case, we can use the ROC curve as a matrix. You can draw receiver operating curve in this way where your false positive rate is on x-axis and then true positive rate on the y-axis, right? And here what we do is we change the threshold, right? So let's say we keep threshold as a 0.5 and then whatever the model predictive probabilities are, right? We count the true positive, false positive, and true negative, right? All four things, and then we according to equations we get a point, we represent it on the graph anywhere, and then again we change the threshold. Let's say now we make it 0.6 and then we get another point and so on. So across different thresholds we map it on this graph, and we get either curve line or straight line based on the points we got, right? So ideally we should want higher true positive rate, right? So this is the ideal graph we want in any case. And basically we calculate the area under the curve. So basically this is the area under the curve, it's called AUC. So the higher the AUC, the better it is. And what ROC curve does here is ROC AUC score tells us is how the model is better at distinguishing your positive versus negative class. If we get, let's say, straight line like this, it means model is not confidently distinguishing for positive versus negative. It's randomly, there is a 50% probability of getting positive versus negative. So it's not a better way. So model, basically model is not doing pretty good there. So yeah, and you should use this ROC score when your data set is balanced, right? When you do care about the both false positive and false negative errors, and you want to make sure both are kind of balanced. And when your data set is imbalanced, right? In that case, you can use PR-AUC score, which is better compared to ROC score. So usually when you're, let's say, yeah, what does the data imbalance mean? Where, for example, you have very few examples of positive class compared to your negative class, right? And in that case, you would like to go for this. Maybe I'll make another video where we can say like why this is better by maybe looking into an example. But for now, you can see here, right? In this case, we are counting true negatives, and in case of imbalance, we will have higher true negatives. So if we have, let's say, method one, model one, and model two, and in this case, if we have higher true negatives, right, because denominator is higher always in this case, so there won't be much difference between false positive rate in both the models. But if you look at here, right, there is no true negatives we are covering. So in this case, it doesn't play a part, and we can get a higher difference between this between method one and method two, or model one and model two, you can say. and that's why we use PR curve. And similarly, as ROC curve, here we are getting different thresholds, right? Then we are mapping the graph. Similarly, in this case as well, we get different thresholds, and based on that we draw this graph. So we have now the last matrix, which is F1 score, which is harmonic mean of precision recall. But only difference is this also can be used in case of imbalance data set. But if you look at this, right, here our threshold should be fixed. Let's say here our threshold is zero point 0.5, and then at this particular threshold we get the F1 score. So if you already manually figured out like what should be the threshold for your problem, then you can go for F1 score for monitoring. But if you are not sure, like between multiple models and plus you are not sure what should be your threshold, so you can draw your graph across multiple thresholds and get it. And this is the ideal graph, but yeah, I mean, you may get this kind of graph, this kind of graph, or any different graph, and then based on that you again vary under the curve and see which I mean whether your model is doing better or not. So hope you get it like this. F1 score, you use it when your threshold is fixed, and you use this PR curve when basically your data set is imbalanced and you want to distribute or look at the trend across all the thresholds and then decide what to do or with the model, right? So yeah, this is all I think about all the classification metrics. In future, if I in detail make a video of any of the metrics, I'll drop a link in maybe descriptions. And yeah, please feel free to comment or give me any feedback so that I can improve upon my videos in future. And hopefully all of the metrics, right, you can use it to objectively decide like which metrics to decide in your system design rounds or maybe your ML concept rounds and so on. If you have watched this video until end, so this is a bonus summary for you, which classification metrics to choose basically based on the problem. So if you have balanced classes in the data set, and if you think the false positive and false negatives are equal, then you can use the accuracy. If you think the false positives are expensive, for example, in spam detection, uh, uh, putting or labeling important email as a spam can be very costly. So you can use precision in that kind of problems. If you think false negative are costly, then you can use recall. So for example, if you say if someone has a cancer, and then if you wrongly say that person doesn't have a cancer, that could be expensive in for this cancer detection problem. So for such problem you can use the recall. If you think the true negatives are important for any problem, then you can use the specificity as a matrix to evaluate that model. If you think the classes are balanced, and you want to distinguish how your model is predicting positive versus negative, or how better it able to discriminate positive versus negative classes, then across the and that to across the threshold, then you can use the ROC-AUC score. If your data set is highly imbalanced and you have very few examples of positive classes across the and you want to evaluate the model across the thresholds, right, then you can go with the PR-AUC score. And if you have decided the threshold already and your data set is imbalanced, then you can go with the F1 score as your evaluation matrix. So this is all it, and thank you very much for watching this video throughout the course.